Let's record just in case I say something useful. Today we want to talk about divergence and curl of a vector field. We want to see where this sits in our calculus thinking. In our calculus thinking, we're going to think of divergence and curl as derivatives. They're going to fit in that slot as derivatives. It's going to be a thing that happens at a point. So if we think about our original OG derivative, the slope of the line tangent to a curve at a given point, we're just trying to calculate the slope, but with 1 point. So slope is change in y divided by change in x. And the tangent line is what happens when the change in x goes to 0. So we're really calculating, we're trying to figure out what 0 over 0 we're dealing with when we're trying to find the slope of the tangent line. Delta y is 0, delta x is 0. What 0 over 0 are we getting? Is it some constant? Is it infinite? Or is it 0? Now, in our thinking about divergence and curl, we introduced the del operator, something that we actually introduced when we dealt with the gradient. But the del operator just applied to a scalar function will produce the gradient. So the gradient was del f, where f is a scalar function. So del is this vector. If we apply it to a scalar function, we get the vector called the gradient. The gradient does tell us things. It tells us the direction of maximum increase for our function. It tells us the direction of maximum increase for our function. So we also want to remind ourselves of the single variable version of this del operator, which is d over dx. It just says take the derivative with respect to x. But when we have only one variable, we don't have partial derivatives, we have the derivative with respect to x. So that's kind of the early version of the del operator, although not really. Don't at me in the comments because I turned comments off. So yesterday we talked about the divergence of a vector field, and we want to think of the divergence of a vector field as the flux density at a point. That's the other part of that makes this a derivative type of thinking. The other reason we're thinking about derivatives, it's the flux density at a point. So we calculate this by looking at a small sphere, could be whatever shape we want really. Some small closed shape, sphere is easiest, around a point. And we calculate the vector field, the flux of the vector field through the surface of that sphere. And then we do the calculus thing and shrink it down to a point. When we shrink the volume down to a point, and then the volume is 0, we can't divide by 0, but we get 0 over 0, and that's the same kind of slope problem that we had before. So that's the thinking about the divergence. It's at one point, how much of the vector field is kind of pushing out or slurping in. So we call that the divergence. We think we can define it as flux density at a point. Take the surface integral, a flux integral, and divide by the volume of this contained by the surface. I wrote volume of S. I mean volume contained by S. That would be, because S is a surface, and so it has no volume. So maybe we should say volume contained by S. Still calculating, it makes sense that we call it a density because density says how much is there divided by how much space it takes up. We're calculating how much flux is there and dividing by how much space that flux takes up. So the cool thing is that our del operator, if we find the dot product of the del operator and the vector field, that will give us the divergence. That will tell us the divergence at a point. Just like when we want to find the derivative, if we apply our derivative operator to a function, that will tell us the slope of the line tangent to the curve at any point. That's the magic part. So in an effort to be predictable, we want to calculate, we want to see this kind of structure in our discussion of curl. So we're going to start off with circulation density. This is going to be applied to a vector field, and this is going to be at a point. In the divergence, we have a flux integral divided by a volume. In this circulation, we're going to be doing the same thing. Although in our circulation is going to be how the vector field flows around an area. That's how we want to think about circulation density at a point. How the vector field is flowing around a point. That's a hand-wavy way of thinking about it. So imagine the right-hand rule. We have U cross V. We put our fingers in the direction of U and curl them the short way to V, and then our thumb is that normal vector. How much normal vector are we getting? When we find this cross product, how much of normal vector are we getting? Is it a really big vector because the vector field is flowing really hard around a point, or is it a really small vector because it's slowly flowing around a point? This is not a great description, it's just kind of a feeling description. Just trying to get a feel for what's going on. How is the vector field flowing around a point? So our circulation we're going to look at the circulation around a curve. We're going to imagine a curve that contains a region, which sounds a lot like Green's theorem. There's a curve surrounding a region. We're looking at the vector field flowing around that curve. And since we're making a density, we're going to divide by how much space it takes up. So we're going to divide by the area contained by C. So we're going to have a circulation of our vector field F. We're going to take the line integral of the vector field around the curve. And we're going to divide by the area inside C. I don't know why I made this so small. It's fine. And then so this is our circulation density. Instead of taking the flux through a surface near a point and then shrinking the surface down to a point, we're going to look at the vector field. We're going to take the line integral of the vector field and divide by the area inside C, and then do the same thing that we always do, make it into a 0 over 0 problem by taking the limit as the area goes to 0. So if we have a point, then our line integral will be 0, and our area inside will be 0. We have a 0 over 0 derivative, like we always have. Now we want the now we have the vector field in R3, and we can imagine a curve going around in any kind of direction. So this is going to be the circulation around some normal vector. So here's going to be a vector going off in one direction. I want to look at the circulation of the vector field around that vector. And it's like you're going to attach a paint stirring tool to your drill. The normal vector is the direction that you're sticking the drill into the paint stirring thing. So here's a normal vector, and I want the circulation. Here's a normal vector, and I want the circulation around that vector. Here's another normal vector. I can calculate the circulation around that vector by putting a little circle around that vector, and calculating a line integral around that circle. Divide by the area of the circle, and let the area of the circle drop down to 0. So this is the circulation density of a vector field at a point in a direction. In R3, if we want to define some circle, I have to know what this circle is perpendicular to. In R3, this wasn't necessary for divergence, because if we have a sphere, then we're looking at the flow through the sphere. But at a point, which circle are we looking at? So C, I wrote point up here. So if we have this point, I could have a small circle C, and that would be with this normal vector. Or I could have some other small circle, let's say going in this direction. So we can see that C1 and C2 are different circles around that these two different normal vectors at that point. All right, so we have at a point, there's all kinds of different directions we could establish a normal vector. There's all kinds of different directions that we can establish a normal vector at a point in R3. We can point in any direction, all the way around for 360 degrees in theta and 180 degrees in phi, if we think of this in terms of spherical coordinates. So the curl is one of these circulation vectors. the curl of a vector field at a point is the direction for which the circulation is a maximum. So the curl, similar to the gradient, it's got the definition similar to the gradient, is the direction for which the circulation is greatest. It's the direction in which the circulation is greatest. It's the direction n for which the circulation is greatest. The magnitude of the curl is the circulation density around that direction. So the magnitude is the circulation density. It's our maximum circulation density. At the point. It's our maximum circulation density. Curl is very much like gradient. It's a direction telling you which way to go for maximum circulation. Just like the gradient is the direction to go for maximum increase. And the magnitude of the gradient is the amount of increase. The cool thing here is that if we want to calculate the curl, if we want to figure out the direction in which our circulation is greatest, we get to use the del operator. It's a derivative after all, a derivative type of thing after all. And we just find the cross product of the del operator and our vector field. So we've got this del operator. We can combine it with a scalar function, and we can multiply it by a vector field in two different ways: dot product and cross product, and each of them have some kind of relevant definition, some kind of meaning. The two that end up being vectors are some kind of vectors indicating the direction of maximum something. So the gradient is the direction of maximum increase of our scalar function f. The curl, del cross f, is the direction of maximum circulation density. Just like the magnitude of the gradient is the maximum increase of the function at a point, the magnitude of the curl is the maximum circulation density at a point. It tells you which direction is the maximum circulation density. We haven't talked about what we can do with divergence and curl. We've just talked about where they sit in the story of calculus and how they act as derivatives. And so I'm going to skillfully avoid talking about what we do with them so that I can fit them into our bigger picture of calculus. So gradient, divergence, curl, we're thinking of these things as derivatives. We're thinking of gradient, divergence, and curl as derivatives. I'll put this in quotes, as we're trying to get a feel for things. It makes sense. We're trying to calculate some kind of 0 over 0. There's some 0 over 0 stuff going on here. So now we want to think about where derivatives fit in our fundamental theorems, in our structure of a fundamental theorem of calculus. Remember, we have the fundamental theorem of calculus structure is that we integrate a derivative over a set. We integrate the derivative over a set by evaluating the function on set, on the boundary of the set. Our fundamental theorem of calculus structure, we integrate the derivative of a function over a set by evaluating the function at the boundary of the set. We saw this on our original fundamental theorem of calculus. Where we integrate a derivative over an interval by evaluating the change in the function at the boundary of the integral or interval from a to b. The set over which we are integrating the derivative is the interval from a to b, so the boundary of that interval is the points are the points a and b. In line integrals, we have the integral over any path from point P to point Q. The gradient, that's our derivative in this line integrals fundamental theorem, dot dr. So we're doing a line integral of a gradient field, and we can just evaluate the potential function at the endpoints. The potential function is the same, that's potential in the same context as potential energy. And we're just looking at the potential difference in the potential at the endpoints, potential function at the endpoints. I might have said things a little bit off there because physics is weak for me. So we also have Stokes' theorem. The derivative that's involved in Stokes' theorem is this curl derivative. If we integrate over some surface S, the curl of a vector field, we can calculate the vector field at the boundary of oops. Oh, right. We evaluate the vector field at the boundary of the surface. We didn't talk completely about the setup for Stokes' theorem. But C is going to be the boundary of some surface S. Just like P and Q are going to be the endpoints of some curve C. Just like A and B are the endpoints of the interval from A to B. And then we also have the divergence theorem. If we integrate the divergence of a vector field over a solid W, so at all the points inside a solid W, we can just evaluate the flux of that vector field through the surface of the solid W. So in this case, S is the surface of solid W. C is the boundary of surface S. P and Q are the endpoints of the curve C. And in our original, A and B are the endpoints of the interval from A to B. Divergence, curl, gradient, and derivative. Those are all in the category of derivative. That's the structure of the fundamental theorems of calculus. So these are the things that you want to think about. You want to think about the divergence as the flux density, flux through a sphere at a centered at a point, and then shrink the sphere down to a point. We want to think of the curl as the maximum circulation density, the direction with the maximum circulation density. Circulation density being looking at a circle around a normal vector at a point, a circle around a normal vector at a point, and then we want to shrink the circle down to a point. We want to think of the curl and the divergence as derivatives, and that gives them their place in our fundamental theorems of calculus. So think about those things, and we'll come back and talk about these calculations, how to make these calculations, and what we can do with some divergence and curl. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.